everybody. Today we're going to continue with linear kinematics now that we've learned how to do vector addition for perpendicular and for collinear vectors. In fact, we'll be looking at how that applies to this today. Now, let's first define what acceleration is, okay? Acceleration, let's go ahead and write that out. Acceleration is also a rate, and we use a lowercase letter a for acceleration, and it is a rate of change in velocity. Now, what is a rate again? Oh, a rate is a ratio with time in the denominator. So if we want to write this sentence, this definition as a mathematical formula, we would say acceleration is, so acceleration is, we're just converting math into English, or should I say English into math, sorry. Acceleration is the rate, so we write a ratio with time in the denominator, but what goes in the numerator? The last part, change in velocity. Change in velocity. So acceleration is the rate of change in velocity. So in other words, it's how fast you change your speed, okay? We could also write it this way. Change, if you'll remember, delta means to find a difference. You're going to find the difference between the velocity you have now and the velocity that you did have. So that would be the final velocity minus the initial velocity or original velocity. I don't care if you use a VI or V sub O. I get so used to doing V sub O in AP Physics that sometimes I use that here. But if you want to use V sub I for initial, that's okay too, or you can say O for original. But here we go. And this is normally what I have written on the board for my students for testing. All right, I just say the rate of change, which is a difference in velocity, is the acceleration. Now, it is a vector quantity, so that means it has magnitude and direction, which we'll look at in a minute. But let's first talk about what acceleration actually is. Most people don't really understand what it is, so I want to talk about it a minute. Acceleration is the change in velocity that you have from one point in time to the next. So if you look at each second, it would be the change from one velocity to the next in that second. Okay? Now that means each second you're going to change your velocity by some increment. I like to use the term increment. So what acceleration actually is, it's the increment, the numerical value by which we increase or decrease, because you could take it away as well as add it, the velocity each second. It's the increment by which we increase or decrease velocity each second. How do we measure acceleration? Well, as you know, in SI, velocity is measured in meters per second, and we're dividing that by time, which is measured in seconds. So you get a meter per second per second. But that's the same thing as saying meter per second squared. And some people are thinking, well, how do you get meter per second squared from this right here? Well, you've got a ratio over a whole number. Now remember, you can think of a whole number as being over 1. So actually, you've got two ratios being divided. And if you'll think about it, you learned a little trick in your math class that says if you've got two ratios that you're dividing, you can take the first one and multiply by the reciprocal of the second one. So if you say meters per second times 1 over seconds, you get meters per second squared because the seconds will be multiplying each other. Okay, so rate of change in velocity, meters per second squared. That is the acceleration. Now what we're going to do is we're going to look at some of the kinds of acceleration that we have, okay? The first one I'd like to look at today is uniform acceleration. Now, sometimes you will see authors and scientists call it constant acceleration, but I'm a little hesitant to use the term constant. A lot of us actually use the word uniform instead of constant. That's because in uniform acceleration, this increment, this difference from one point in time to the next, it's always uniform. That means it stays the same value, okay? Which seems a little more different than constant acceleration, all right? Uniform acceleration, the velocity increases or decreases by the same increment during each unit of time, okay? The same increment. Now, there is a classic acceleration due to gravity, and the acceleration due to gravity is a classic uniform acceleration. So let's put that down here as an example. G, the acceleration, I'm writing small because I got more stuff to put here, acceleration due to gravity. Now, here's what we need to understand. That little g, that does not mean gravity at all. In fact, I always am a little worried about the fact that they use a little g to represent the acceleration, the change in velocity per second for acceleration. They use a little g for that instead. People think that's gravity. No, it's not. It's a change in motion. Gravity is a force, so we designate it with an F. This is a little g. It's the acceleration that gravity produces. So, if you have an object that is in free fall, and being in free fall simply means that there's no force acting on the object other than gravity. So, say you drop a ball off the roof, okay? You go upstairs and maybe you take a golf ball and you drop it off the roof, okay? It will accelerate to the ground by uniform increments, and those increments have a special value on Earth. On Earth, those increments are 9.8 meters per second squared. So that means every second that the ball falls, its velocity increases by an increment of 9.8. So when you first release the ball, it's at rest, and it must begin to move downward. Gravity pulls it down and begins to accelerate it, and it will go from 0 to 9.8 in the first second. In the next second, it will go from 9.8 to 19.6. And in the next second, it will go from 19.6 to 29 point something. Okay, I can't seem to add in my head right now. But in any case, so every second the velocity is going to increase by this increment. The same goes for something that is thrown straight up. So let's suppose you take the golf ball and you throw it straight up. The moment it leaves your hand, so that no more force is acting on it from your hand, the moment it leaves your hand, only gravity is acting on it. Gravity pulls down, and since the ball is moving up, gravity will begin to slow the ball by increments of 9.8. Whatever velocity it had when you let go, that velocity each second will decrease by increments of 9.8 until somewhere up there it stops for an instant. And then the velocity changes direction and it will begin to accelerate back down, adding those increments of 9.8 back until when it reaches the level where you released it, it'll be traveling just as fast as it was when you released it. Okay? Now, let's talk about the fact that sometimes gravity can slow objects down. In fact, many objects can slow down. If you look up, if you're driving your car down Manatee Avenue and you look up and you see a red light, all right, what do? Well, you got to stop. So you begin to decelerate. You step on the brake, don't you? So let's talk for just a moment about deceleration. And deceleration actually only has one C. Acceleration has two, but deceleration only has one. Deceleration is an acceleration which causes your velocity to decrease. It decreases your velocity. Now, how can it do this? Simple. It has to point. It points the opposite direction from your velocity. Okay? It points the opposite direction. All right? Now, so let's look at this right here. And I don't have a lot of room right in here, so I'm going to just draw an arrow upward, and we're going to look at it up here. Now watch this. Let's suppose that to the right is positive, to the left is negative, just like on the x-axis. To the right is positive x hat, to the left is negative x hat. Let's say that you're traveling with some velocity to the right in the positive direction, and you want to accelerate. Well, you need an acceleration increment. Okay, so let's say you choose an acceleration increment. Doesn't have to be very big. There's your acceleration increment, tiny little arrow right there. So what this means is that every second, you're going to take this, put it tip to tail with this one, and it's going to make your velocity that much bigger. And then the next second, you add it again. And then the next second, you add it again. And then the next second, you add it again, such that your resultant velocity continues to increase. So your acceleration is your increment of increase in velocity. And notice, to accelerate, they must point the same direction. So it points same direction. To accelerate. All right, points the same direction to accelerate. But what if you want to slow down? You look up ahead and ooh, all right, the light is red and you want to slow down. So here's your velocity now. And now you want to slow down. How do you do that? How do you make this vector smaller? Oh, you take the increment and you turn it the other way. So let's say now our increment of acceleration points in the negative direction. So now what happens when you add it to this? You end up subtracting, and that makes this one smaller. So what you do is, 1 second you take away this, and then the next second you take it away again. The next second you take it away again, until all that you have left is a smaller velocity, or until you get to the red light and stop. Okay? So acceleration and deceleration are actually both acceleration. It's just that when you want to speed up, they have to point the same direction. When you want to slow down or decelerate, they have to point the opposite direction. I hope that helps explain acceleration versus deceleration. Be very careful about calling a deceleration a negative acceleration. That can be dangerous, because suppose that you were traveling in the negative direction instead of the positive direction, and you had a negative acceleration. Well, they point the same way. So you're not decelerating. You have a negative acceleration rate, but you're not slowing down, you're speeding up. Your velocity is getting bigger. So don't think that a deceleration is always a negative acceleration. That's not true. In this case, you have a negative acceleration increment, but you're speeding up, you're accelerating. So be careful. Simply realize that to speed up, to accelerate, the two vectors have to point the same direction, like here and here. To slow down, they have to point opposite directions so that you take away from the velocity, regardless of whichever way the velocity points. The acceleration has to point the opposite direction in order to take away from the velocity. Okay? All right, so uniform acceleration simply means that this increment that you're going to add to the velocity is always the same increment. Okay? Now, can you add increments that are different, that are changing all the time? Certainly. But that would be considered non-uniform acceleration, and to deal with non-uniform acceleration requires the use of calculus. So we don't usually deal with it very much. However, we can sometimes talk about average acceleration. Average acceleration. This is when we would take all the increments, if they're different, and we would simply average the increments to see what your average increment of increase or decrease in velocity is. Okay? You use the same formula. You're just going to talk about the average increment. But we don't usually look at the increments in average acceleration. We just see what the average is. We don't worry about whether this one's bigger than that one or something like that. Finally, the very last one, we've got uniform acceleration where the increments are the same. We've got average acceleration, which is the average of the increments when they're not the same. And then we can also have, I wonder if anybody knows what this is. Instantaneous acceleration. I wonder what that means. Like, we've not heard that before. Instantaneous means one point in time. So, instantaneous acceleration is your acceleration at a single instant or point in time. Okay? And we're going to be looking at it on a graph in just a minute. We'll look at all of them on the graph. So let's talk about graphing acceleration. And let me back up a little bit so you can see it a little better. That'll be helpful, I'm sure. Now, we're going to diagram a graph here, so there's some things we want to put on here. But first, let's understand what it is we're graphing. I'm taking our definition of acceleration from up here, and I'm solving for the change in velocity. So now this formula is of the form y equals mx plus b, a linear form. So if we plot the velocities on the y-axis and the time on the x-axis, then the slope of a velocity time graph is the acceleration. So let's write that down here. The slope of the velocity time graph is the acceleration. Okay? Now, we need to understand something. We've already looked at one particular type of motion graph, and that is the position time graph. And when you had a position time graph, you looked at where the object was located at each point in time. That's not what you're doing here. But yet people try to read a velocity time graph as if it were a position time graph. You must be so careful not to do that. Think about this. If this is a velocity time graph, we're looking at how fast the object is moving at each point in time, not where it's located. So you know what that means for the directional quality? That means we look at it differently. Up the graph and down the graph are no longer positive and negative. We have to show change in direction here a different way. We're going to look at that, okay? But first we need a graph to analyze. So here's what we're going to do. First, let's scale our axes. We're going to go, it looks like I went by threes right here. 3, 6, 9, 12, 15, 18, 21 seconds. Okay, and on the y-axis, we're going to go 2, 4, 6, 8. Down here, -2, -4, -6, -8. Okay, we're going to make a graph, and you'll probably want a straight edge for this. I'm going to see if I can, here, I've got a straight edge. Yeah, I've got a little one. Okay, so make a point at the origin, and now make another point at, let's see, where does this go to? It goes 6 and 8. Okay, so over to 6 and up to 8, make another dot, and we're going to connect those with a straight line. Okay, just like boom, that. Okay, all right. Now, I want you to make another dot at 9 and 8. So if we go straight up to the same velocity at 9 seconds, and we're going to connect those two with a line, just like that. Now, I want you to, oh, this is going to be a big one. We're going to go to about, it looks like we're going to go to 15 and -8. And what we're going to do is we're going to take our, there we go. Take that, and we're going to connect those 2 points. And while we're at it, make a point right there where it crosses the y-axis. That's an important point. We'll be talking about it soon. Make one more point at at 18 and -8. I don't know why I did it this way, but I did. Just looks like the mirror image, more or less. Just below the x-axis instead of above. And then the last one we're going to do goes from that point over here to 21 seconds on the x-axis. Just like that. Okay? All right, so take a moment to do that. If you need to, pause the video and look at the picture and draw it, and then come back. Okay? So now, to get started on this, first we're going to label each of these sections so we can talk about them and describe them a little more easily, okay? Let's see here now. Right here, did I get all of, yes I did, okay. So right here, we're going to call this section A, and this will make it easier to talk about them. Section C, now believe it or not, from here to here, we're going to call this section D. All right? I know it looks like the same thing's going on, but it's not. All right, let's call this E, and this one F. All right? Now, let's take a look right here. All of these, here we have positive slope, zero slope, negative slope all the way down to here, zero slope, and positive slope again. Now, the slopes are the accelerations. If you use the slope formula, y2 minus y1 over x2 minus x1, you get the slope of each section, and I want to write this down over here, okay? Write this down over here. This is very important. The numerical value, the magnitude of the slope is the magnitude, that is numerical value, of the acceleration. So if you use the slope formula and you find out this has a slope of, well, if we say 8 over 6, what is that, 1 and a third? No, 1 and a fourth, I think. Something like that. All right, in any case, that would be the acceleration increment. That would be the increment that you're going to add or take away from a velocity. Now, in this case, that slope is positive. So you have a positive acceleration increment. And look over here on the y-axis. You're adding it to a positive velocity. Well, what happens when you add positive pieces to a positive vector? You get a bigger and bigger vector. You start out from rest. Right here, it goes to 2, 4, 6, 8. Get the idea? This is not where you are. This is how fast you're going. So you are increasing your velocity here. Okay? In fact, if I remember right, if you find the slope, the acceleration here is positive 1.3, I just saw it on my key, meters per second squared. So you're adding 1.3 to each of these every second. Okay? And remember, a second is only a third right here. So now, that's what the magnitude represents. And then the sign that we just talked about, the sign of the slope, is the direction of the acceleration increment. So it tells you this one's pointed forward. This increment points that way. Just like these little increments right up here. They point to the right, okay? They're positive. So you've got a positive velocity and you're adding positive increments to it, so your velocity gets bigger, okay? Now, let's write this down. And I know we don't have a lot of room, but we're gonna steal some room. We're going to steal some room right over here, I think. Let's just do it right over here. Section A. Section A, you have increasing velocity that's in the positive direction. How do I know? Oh, look over here on the y-axis, because that's where the velocities are. Not position, velocities. You have an increasing velocity in the positive direction. Okay? Here's the direction of the object's motion. It's actually moving in the positive direction, all right? And the velocity is increasing because you have a uniform, positively directed acceleration increment. Now, how do I know it's uniform? Because that's a straight line. Every point on that straight line has a slope of 1.3. So for this entire time period, you are adding the same increment to that velocity, okay? So it's a uniform, positively directed acceleration, and that's why the velocity is increasing. All right, let's talk about section B now. I want you to look. We have zero slope. If we have zero slope, we have zero acceleration. But does that mean you're not moving? No, because look, you have a velocity of 8 in the positive direction. The thing is, it stays 8 for 3 seconds. You've got 8 meters per second, 8 meters per second, 8 meters per second, 8 meters per second. So your velocity is staying constant. You're not at rest here because this is not position. You're moving. That's a big difference right there. People look at the zero slope and they want to think, oh, the object's at rest. Not on a velocity time graph, no. The only place you can be at rest on a velocity time graph is right here on the x-axis where the velocity has a value of 0. This is the only place you can be at rest. So right at 0 seconds and at 12 seconds, your velocity is 0. Oh, and at 21 seconds, your velocity is 0, but not here and not here, okay? 0 slope, 0 acceleration on a velocity time graph, okay? So part B, we have constant velocity in the positive direction, no acceleration, okay? All right, now, here's the fun part. This is where people really freak out. They want to look at this entire line and say that the object's going in the negative direction? Absolutely not. If this were a position time graph, that would probably be true. But this isn't a position time graph. It's a velocity time graph. And look right here. These are all positively directed velocities. This down here, these are all negatively directed velocities. So somewhere you changed direction. Guess where it was? It was right here where you stopped. Now look, everybody look. We start right here at 9 seconds. We're moving at 8 meters per second. Then we decrease to 6. Then we decrease to 4. Then we decrease to 2. And then we stop. And right here's where we turn around, because we left something at home. And then we increase velocity to 2 in the other direction. We increase our velocity to 4. We increase our velocity to 6. We increase our velocity to 8 in the other direction. You get it now? This is no longer where you are. It's how fast you're moving and in what direction. If you're above the x-axis, you're moving in the positive direction. These are positively directed velocities. Because look, it says it right here. Positive 6, positive 4, positive 2. These are positive velocities, okay? Now the slope, how steep it is, and you can see it's a lot steeper than this one. The slope is the acceleration. In fact, if we were to determine the acceleration here, I think it's, I'm not sure what it is, but in any case, right here, we have an acceleration that has a negative direction, and it's, let's see if I can figure it out. 9 minus a negative 8, that'd be 17 divided by 6, so that's going to be almost 3. So it's going to be like 2.8 or 9, I'll say 8 for right now, 2.8 meters per second squared. What does this say? That means every second you are going to subtract 2.8 from whatever the velocity is on the y-axis. So right here we started at 8. For 1 second, we subtract 2.8. Then the next second, we subtract another 2.8, then another 2.8, then another 2.8, until we stop. Then we change direction. Now we're going to be moving in the negative direction, but we're still going to subtract increments of 2.8. It's just now we're going to be subtracting from negative velocities. So the value of the velocity gets bigger because they point the same way again. All right? Two vectors pointing the same direction. A negative velocity, a negative increment, you get a bigger velocity. That is what's happening from 12 seconds to 15.